A voltage source maintains a constant voltage across its terminals, irrespective of the load connected to it. It acts like a battery, providing a push of electrical energy. Voltage sources are characterized by relatively low internal resistance. Examples of voltage sources include batteries, AC power outlets, and voltage regulators. Conversely, a current source provides a constant current through its terminals, regardless of the voltage across it. Think of it as a pump pushing electrons through a circuit. Current sources are characterized by relatively high internal resistance. Examples of current sources include solar cells, current-limiting resistors, and constant current power supplies. The key differences between voltage and current sources lie in their control variable, internal resistance, and circuit response. Voltage sources control voltage, while current sources control current. Voltage sources have low internal resistance, while current sources have high internal resistance. When connected to a load, voltage sources maintain a constant voltage, while current sources maintain a constant current. Let's consider some practical examples. A battery in a flashlight serves as a voltage source, providing a constant voltage to power the light bulb. On the other hand, a constant current power supply is used to charge a battery at a specific current rate. In some cases, a source can exhibit characteristics of both voltage and current sources. For example, a solar cell can act as both a voltage and a current source, depending on the load connected to it. To further illustrate the difference, let's use an analogy with water flow. A voltage source is like a water pump that maintains a constant water pressure, regardless of the size of the pipe it is connected to. A current source, on the other hand, is like a water faucet that releases a constant flow of water, regardless of the height of the water tank. Understanding the concept of internal resistance is crucial to differentiating between voltage and current sources. Internal resistance is the opposition to the flow of current within the source itself. A voltage source is designed to have a low internal resistance so that it can deliver nearly its full voltage to the load. If the internal resistance were high, a significant portion of the voltage would be dropped within the source, reducing the voltage available to the load. A current source is designed to have a high internal resistance. This high internal resistance ensures that the current remains relatively constant even as the voltage across the load changes. The high internal resistance minimizes the effect of load variations on the output current. In practical circuit design, the choice between a voltage source and a current source depends on the specific application. Voltage sources are commonly used to power electronic devices, provide reference voltages, and establish stable voltage levels. Current sources are often used in applications where precise current control is required, such as charging batteries, driving LED, and biasing transistors. It is also important to consider the limitations of real-world voltage and current sources. Ideal voltage and current sources are theoretical concepts. Real-world sources have limitations, such as voltage droop under heavy load for voltage sources and current variations with voltage changes for current sources. These limitations should be taken into account in circuit design to ensure proper circuit operation. The concept of source impedance, which includes both resistance and reactance, is also relevant. In AC circuits, the source impedance affects the voltage and current delivered to the load. Matching this source impedance to the load impedance can improve power transfer efficiency. In summary, a voltage source maintains a constant voltage, has low internal resistance, and is analogous to a water pump maintaining constant pressure. A current source maintains a constant current, has high internal resistance, and is analogous to a water faucet delivering constant flow. Understanding these differences is fundamental to analyzing and designing electronic circuits. Further exploration of voltage and current sources can involve examining their use in specific circuit configurations such as voltage dividers, current mirrors, and operational amplifier circuits. These circuits rely on the characteristics of voltage and current sources to perform specific functions. For instance, a voltage divider uses resistors to divide a voltage source into smaller voltages. A current mirror replicates a current from one circuit to another. Operational amplifiers use both voltage and current sources internally to amplify signals. The behavior of voltage and current sources can be modeled mathematically using circuit analysis techniques such as Kirchhoff's voltage law and Kirchhoff's current law. These laws allow engineers to predict the voltage and current in a circuit based on the source characteristics and the circuit components. Simulation software can also be used to model and analyze circuits with voltage and current sources. These tools allow engineers to test different circuit designs and optimize their performance before building a physical prototype. In addition to the applications mentioned earlier, voltage and current sources are used in a wide range of electronic systems, including power supplies, signal generators, and control systems. Power supplies convert AC voltage to DC voltage and provide regulated voltage and current to electronic devices. Signal generators produce various waveforms, such as sine waves, square waves, and triangle waves, which are used for testing and measurement. Control systems use voltage and current sources to control the behavior of machines and processes. The selection of a voltage or current source depends on the specific requirements of the application. Factors to consider include the voltage or current level, the accuracy and stability required, the power consumption, and the cost. It is also important to consider the environmental conditions in which the source will be used, such as temperature, humidity, and vibration. Voltage and current sources are essential building blocks in electronic circuits and systems. A solid understanding of their characteristics and applications is crucial for any electronics engineer or technician. By understanding the concepts discussed, one can analyze, design, and troubleshoot a wide range of electronic circuits and systems. The ability to differentiate between voltage and current sources, understand their internal resistance, and apply them in practical circuits is a valuable skill in the field of electronics. Remember that while ideal voltage and current sources are theoretical constructs, they provide a useful framework for understanding the behavior of real-world sources. By accounting for the limitations of real-world sources, one can design robust and reliable electronic circuits. Continue to explore the applications of voltage and current sources in different circuit configurations and systems. This will deepen understanding and enhance practical skills in electronics. Furthermore, consider delving into the mathematical models and simulation tools used to analyze circuits with voltage and current sources. This will provide a more rigorous understanding of their behavior and allow to optimize circuit designs for specific applications. In closing, the difference between voltage and current sources lies in what they maintain constant voltage or current respectively, and their internal resistance is low for voltage, high for current, which dictates their applications in various electronic circuits. Understanding these fundamental differences is key to mastering circuit analysis and design.